You're watching a Channel 98 NBISD TV production.
Hey, welcome to That Geometry Show. I'm your host, Kevin Corpy. Today is lesson 14. That means we're almost halfway through already with our geometry curriculum. Today we're going to be talking about some fascinating stuff as usual. We're going to be talking about polygons, quadrilaterals, and parallelograms, and we'll even look at some specific names of some of those parallelograms, which will kind of be a little foreshadowing for future shows. So you know the procedure, right? Log on to the internet, www.newbraunfels.txed.net. Click on that geometry show, the groovy icon, get those worksheets, okay, get them out in front of you, work along with me at home, and we'll learn some math together today. Lesson 14, as promised here. It's going to correspond with your Glencoe Geometry Chapter 6.1, and we're jumping all the way to 10.1, which is going to be dealing with a very special application called tessellations. Parallelograms and tessellations. So here we go. By the end of the episode, you should be able to, number one, recognize and apply the properties of parallelograms. And number two, you should be able to recognize beautiful tessellations. Okay? Now, unfortunately, we have no more triangles today. We're kind of done with triangles. After spending what seemed to be about 1,000,000 weeks on them, it's time to kick it up a notch. Okay? Meaning we're going to be talking about something instead of three sides, we're going to talk about a four-sided shape. Now, those triangles belong to a larger family of shapes, basically that consist of a collection of line segments that are joined at their ends, and those are called polygons. Okay? So polygons are just basically the family of geometric shapes that are closed, like triangles and squares. Okay? Now again, today we're going to be looking at one more dimension. Instead of a three-sided, we're going to be looking at a four-sided polygon or a four-sided geometric shape. And in general, any four-sided geometric shape or polygon is called a quadrilateral. Okay, and the name is very apropos because quad means four and lateral means side. So a four-sided polygon is a quadrilateral. This guy right here, who's waving at you, hello, he's a four-sided polygon. He is a quadrilateral. And I don't know why he has such a long face. I'd be a little happier if I was him. Now, there are many types of four-sided shapes. Many types of quadrilaterals, but today we're looking at a very special type of polygon, a very special type of quadrilateral, and that guy is called a parallelogram. Okay, now here's what a parallelogram is. You could probably already get a hint of what it is just by the name. It is a quadrilateral, first of all, which means it has four sides, and it has both pairs, not just one, but both pairs of opposite sides parallel to each other. Now remember from an earlier show, parallel lines never intersect. They basically have the same slope. They run side by side. So a parallelogram is a special quadrilateral, four-sided with parallel sides. So let's look at this example here. This you probably recognize as a special parallelogram called a square. Okay? But notice by the definition, this side here is parallel to this side here. And remember how we denote parallel sides from an earlier episode? We put an arrow on the side, pointing in the same direction. So that means that they're running parallel to each other. So these sides are parallel, and then I'll put two arrows on the other sides, and that denotes that those two sides run parallel to each other. So both opposite sides of this square are running parallel, so a square is a special type of parallelogram. You recognize the green rectangle. The rectangle, by the same argument really, of the square is going to be a parallelogram. This side is parallel to this side, and this side is parallel to that side. Well, these all have right angles, but we can look at a four-sided polygon with parallel sides on opposite ends that is not a right angle. That would be this blue guy here. It's kind of like a rectangle who got tired of standing up, and he's kind of fallen over here. But it still is a parallelogram because if you notice, this side here and the side opposite run parallel to each other. So again, I could put the red arrows, and this side here and this side here also run parallel to each other. I can kind of take that blue shape, I can kind of shorten one of the sides up and tilt it to make it look like this orange fella over here, who is another type of parallelogram. This side here is parallel to that, and this side here is parallel to that side. Okay? This guy, again, just to call out these special names, you know him to be a square. This guy is a rectangle. And this guy here the sides are the same length, and it's not a right angle. This guy, we'll talk about him in a later show, but he's called a rhombus, which is a pretty cool name. And this guy here doesn't have a special name because his sides aren't equal. Okay? But he's still a parallelogram. That should make him feel good. All right. Now, parallelograms, as you probably imagine, have some very important properties. What geometric shapes don't? Okay? We've studied these things, and we've come to realize these properties about them. So I'm going to pass them on to you. Here's what we know. Opposite sides of parallelograms are congruent. So remember, that means they have the same length. So if I come up here to Mr. Rhombus, I know that this side and this side are the same length. They're congruent. I also know that this side here and this side here are also congruent. They're the same length. So again, I can put the tick marks. We also know that the opposite angles in a parallelogram are congruent. So if I come up to Mr. Rectangle, that means that this angle here and this angle here are congruent to each other. And we can know that from a rectangle because they're both 90 degrees. Well, this angle here and this angle here are also congruent to each other. Now in a rectangle, all four are congruent to each other. But if I look at the rhombus here, this angle is congruent to this one, and this angle here is congruent to this one, but they're not congruent to each other. So in any parallelogram, the opposite angles are congruent to each other. All right? These here. Something else we know about parallelograms. The diagonals divided into two congruent triangles. So let me take the rectangle here. A diagonal basically goes from one corner to the opposite corner over here. Vertex. If I do that, I create one triangle, one right triangle in this case, and another right triangle down here. And these two triangles would be congruent. They basically share an angle and a side, okay? And by the right triangle postulate, those are congruent, okay? Well, it works the same thing for any parallelogram. So if I take this blue guy here, this diagonal, which I hope is showing up okay, divides it into two congruent triangles. So this triangle up here, this obtuse triangle, and the bottom one are congruent to each other. Now here's the last fascinating fact about parallelograms. The diagonals, if I drew both of them, they bisect each other. Remember what that means? That means they cut each other into two equal line segments. So let's go back to the blue rectangle. Here's one diagonal. If I carefully draw the other diagonal coming in this way, they bisect each other. They intersect at this point here. But I now know that this line segment is congruent to this line segment. And similarly, this line segment is congruent to that line segment. Okay? So opposite sides are congruent, opposite angles congruent. The diagonals divided into two congruent angles, and the diagonals bisect each other. And you're not going to let me get away with skipping one, are you? I just realized number 3, the consecutive angles are supplementary. There's really no rhyme or reason to listing these, so the fact that I skip one doesn't really hurt. The consecutive angles are supplementary. Remember, consecutive angles are the ones that are next to each other. So if I look at this orange rhombus here, this angle and this angle, they're consecutive angles. They're supplementary, which means that they add up to 180 degrees. So they add to 180 degrees. Well, I could also look at this angle and this one. These two are consecutive angles, and they also add to 180 degrees. Well, that shouldn't be surprising since we knew that these two angles were congruent. Okay? It's a little bit easier to see in something like a square or a rectangle. This angle plus that angle, the two consecutive angles, add up to 180 degrees. Well, we know that because these are right angles, and right angles are each 90, so 90 plus 90 is 180. But it works for things that don't have right angles as well, like the rhombus. Okay? So 5 basic important properties. You've got to memorize those first before you set out to do any work with them. So do the memorization and then do your homework, do your problems. Okay? We don't have time to sit around for you to memorize them because it might take the entire program. So I'm just going to go ahead and start looking at some specific examples. All right? So stay with me here. Okay. Here's an example. In this parallelogram here, we have opposite sides represented by 2x plus 10 and 5x minus 20. Okay? We want to find the length of the unlabeled side. That's this one here. Well, let's see what we have here. We know that this side and this side, because it is a parallelogram, they are congruent, which means their measures are the same. So I can set the two algebraic expressions equal to each other. 2x plus 10 has to equal 5x minus 20. Now, since I have one equation, basically with one unknown x, I can solve for x. So I'll do that. I'll collect my x's on the right-hand side and my numbers on the left. So 5x minus 2x gives me 3x. Adding 20 to both sides gives me 20 plus 10 is 30. Dividing both sides by 3 now, I get x equals 30 divided by 3 is 10. So now that I know that x is 10, I can't just box it up and go to the next problem, because remember, it's always important to answer the question. Now that I know that x is 10, I can figure out what this length is. It's 4 times x minus 1. So that must be 4 times 10 minus 1, which is 39 units, whatever the units may be, inches, feet, miles, furlongs. But how can I use that to help me know what this is? Well, remember, opposite sides are congruent, which means they have the same measure. So if this one's 39, guess what the unlabeled side must be? It must be 39 as well. Okay? Now, if you have the time, it's a good check to make sure that these two sides with your new value of x are also equal. So let's just plug in a 10 for x. 2 times 10 is 20. 20 plus 10 is 30. Plugging in down here, 5 times 10 is 50. 50 minus 20 is 30. So yes, in fact, they are the same length. They're congruent. Another example. If one angle of a parallelogram is 60 degrees, and you can see from our diagram, it's that one there, find the number of degrees in the remaining 3 angles. Oh my gosh. One angle, we're supposed to find the other 3? Well, let's see what we know here. In a parallelogram, remember, the opposite angles are congruent and consecutive angles are supplementary. So they add to 180. So we have to use those two pieces of information to help us find the others. Well, the easiest thing to do is just to immediately label the angle opposite to be 60 degrees. Okay? Notice that it looks to be less than 90. It's an acute angle. So now how can that help me find the other ones? I know that these are going to be congruent. I'll go ahead and put double angle tick marks here because that's one of the properties, but how do I find the measure? Well, I know that consecutive angles are supplementary. So I know that 60 degrees plus this one, or 60 degrees plus that one, have to add up to 180. So 60 plus what number equals 180? Well, let's call this angle A, just to have something to label. So 60 plus the measure of angle A has to add up to 180. Little algebra problem, we'll just subtract 60 from both sides. 180 minus 60, that gives us, not 160, my bad. Just 60. We get A is 120. Okay? So we know that this measure is 120, and so this one also has to be 120 because it's opposite. So is that reasonable? It's always nice to ask about the reasonableness of your answer. This angle appears to be an obtuse angle. Remember, obtuse means greater than 90, and 120 is greater than 90. Okay? And 120 plus 60 is 180. 120 plus 60 is 180. So checking the consecutive angle combinations, we know they add up to 180. All right, here's another nice example. The measures of angle A and B in a parallelogram, A, B, C, D, are in the ratio of 2 to 7. Okay? Find the measures of angle A and angle B. Well, what does it mean to be in a ratio of 2 to 7? We can assume that 2 to 7 means angle A is in proportion to angle B by a ratio of 2 to 7. If we look at the ratio 2 to 7 like this, 7 to 2, where we know that 7 corresponds to B and 2 corresponds to A, if I divide that out, I get 3.5 is B to 1, which has to be A. That means that angle B is 3.5 times larger than angle A. But that's a decimal, okay? And is that reasonable? B certainly looks larger. So how can we use the ratio 7 to 2 or 3.5 to 1 to help us find it? Well, that's where our old friend x comes in. We can use a little algebra. We can let A be 2x if we don't want to work with decimals. Okay, 2 is A, and B would be 7x. Okay, you could have also let A be x and B be 3.5x. Either way, it's just simplifying the ratio. But at least if we call it 2x and 7x, we won't have those pesky decimals. Now, I have them labeled in relation to each other. How can I use these algebraic expressions now to find their actual measures? Well, it is a parallelogram. It was told, or we were told that. So we know that if we add these two consecutive angles, we have to equal 180. So let's do that. 2x plus 7x equals 180. And 2x plus 7x gives us 9x's. How lucky can one guy be? 9x's. Dividing through by 9, we get 180 divided by 9, which gives us 20. Now again, you have an immediate tendency to box up your answer and go to the next problem because you solve for x. In your whole algebraic career, you've been trying to solve for x. But we need to make sure we answer the question. We want to find angle A's measure and angle B's measure. Angle A was 2 times x, so the measure of angle A was 2 times 20, which was 40, and the measure of angle B was 7 times 20, which was 140. Okay, so your teacher will be really, really happy if you write it out like this. The measure of angle A equals 2 times 20, which is 40, and the measure of angle B is 7 times 20, which equals 140. Okay, and a quick check, 140 plus 40 is 180. So you're feeling pretty confident that you've got the right answer. All right, another example. In quadrilateral PRST, the perimeter is 49. If PR is equal to x, notice this is not labeled. I can actually label my quadrilateral now by using the notation here. PR is x, so this must be P, this must be R. RS is x plus 3, so here's x plus 3. R, that must be S. ST is 2x plus 4, so if that's S, this must be T. And a quick check, TP is 3x. So now I have it labeled. Notice this said it was a quadrilateral. It didn't say it was a parallelogram. It didn't say that it was a rectangle. We have no distinguishing marks on our diagram. So we can't assume it's a rectangle. We can't assume it's a parallelogram. We can't really assume those are parallel to each other. All we know is it's a four-sided figure. Now, what the perimeter is, it's our distance all the way around the outside. If we were to walk around the outside, how far would we walk? We know that's 49 units. So I can add up all my variable expressions here and set them equal to 49. So I know that x plus 3 plus 2x plus 4 plus my last one, 3x, has to equal 49. Okay, and the grouping symbols, again, just show the substitution of the different sides, but there's nothing to distribute here, so they're not really needed. So we can start combining up our like terms. We have x, 2x, and 3x to give us x plus x is 2, plus 2 is 4, plus 3 is 7x's. And adding up our numbers, we have a 3 plus a 4, which gives us a plus 7. Now I can isolate my 7x, subtract 7 from both sides, and I get 7x equals 49 minus 7, which is 42. Dividing both sides by 7, I get 42 divided by 7 is 6. Okay, so x is 6. Did we answer the question? No, not yet. Notice that in each of these cases, we have an x in the expression. So we can go through and find the side lengths. Now that x is 6, we know that this side is 6. This side is going to be 9. This side is going to be 6 times 2, which is 12, plus 4 is 16. And this side is 6 times 3, which is 18. So of the 4 sides, 6 is the shortest side. So that would be the answer. But notice how badly this diagram is drawn in relation to what the actual measurements are. It appears to be a rectangle. So it appears that this side is congruent to that side. But in reality, the numbers are what's telling the truth. This side is only 6, and this side is 16, more than twice as big. This side we're calling 9 units, and this side is twice as big, 18. So this diagram is not drawn to scale. Okay? And you need to be very careful. If there's no distinguishing marks on your diagram and it doesn't tell you that these are right angles or that it's a parallelogram or a quadrilateral, you can't assume a thing. And so some tests, especially the SAT and the ACT, will give you diagrams like this, and they're almost trying to deliberately mislead you. Okay? What they're trying to test is if you know that the answers are going to be given the actual size of the diagram and not the unlabeled diagram itself. Time for a break. Let's take a break, watch those public service announcements, and we'll be right back.
So, Sarah, what's going on here? Sarah? Sarah?
She won't answer you. Or she can't.
Why not?
This is the way it's been since she started smoking pot. She's all lazy and boring and... You know, we used to have so much fun together.
And now?
This is what we do.
Hey, welcome back from the break. Let's get right back to it. A couple more examples, and then we're on to my favorite part of the show. Can you guess what that is? All right. I'll give you the answer in a little bit. If ABCD is a parallelogram, so we're back to parallelograms, all those properties, the 5 properties now are going to apply to our shape. And we know the slope of segment AB is 1/3. Ooh, slope is 1/3. Then the slope of CD is ABCD. Eeny, meeny, miny, mo. Which one's right? We don't do it that way. There's no diagram. A diagram is important because it's going to help us orient ourselves. Let's go ahead and draw Mr. Generic Parallelogram. This one will work right here. Okay, so that this side is parallel to this side and this side's parallel to that. So I can start labeling my vertices any way I want. A, B, C, D. Now I can start putting the information on the diagram. Segment AB is here, and the slope is 1/3. So remember, we use M for slope. So the slope of that segment is 1/3. What's the slope of CD? Well, CD, notice, is the segment opposite it. And what do we notice, or what do we know about opposite sides in a parallelogram? They're congruent, and they are also, by definition, parallel. So remember, parallel lines never intersect, and they have the same slope. So if this line has a slope of 1/3, then any line parallel to it, in this case, namely segment CD, will also have a slope of 1/3. Okay, so the answer has to be choice B. Last example here. In parallelogram LMNO, we want to find the values of X and Y. Wow, this is a nice example. It looks like there's a lot of algebra going on in here. All right, let's have a plan of action. We know it's a parallelogram, so we know the opposite sides are congruent. So I know that 3x plus y equals 25. I can create an algebraic expression for that. But the only problem with solving that is it's one equation with two unknowns. And you can't do that. You could solve two equations with two unknowns or one equation with one unknown, but not one equation with two. So we need some more information. Well, let's kind of go on the hunt here. I know that this diagonal bisects this diagonal, so I know that 20 equals 20. Let's write that down. Is that going to help us? 20 equals 20. That's a true statement. It's not going to really help us, though. Let's try the other diagonals. I know it bisects it, so I know that 2x has to equal 16y. 2x has to equal 16y. Well, that one will help us. I can actually take these two equations now, which are different, with two unknowns, and I can solve them simultaneously. In algebra, you learned a way to do that. Linear combination, substitution. Guess and check's not the best way to go. I'm going to do substitution. I'm going to take this equation, I'm going to solve it for x by dividing both sides by 2. So I get x equals 8y. Now I can take my other equation up here, the 3x plus y, and everywhere there's an x, I can plug in an 8y. So we'll do that down here. So I'm going to get 3 times x, which is 8y, plus y equals 25. And what that allowed us to do is to get our equation now, one equation in terms of a single variable, y. And it didn't matter which variable up here we solved for. I chose the more convenient variable. Now I can multiply these together. 24y plus y equals 25. So that's 25y is equaling 25. Dividing both sides by 25, we get y is equal to 1. Now in this question, it asks us to find x and y. So we found y. We're halfway through. How do we find x? Well, the nice thing about substitution is before you make your substitution, that first equation that you solved for x, he will always be ready to go to plug your new value of y that you found back into it. So we can find x just by plugging in. So x is 8 times y, and I just found y to be 1, so I know that x is 8. Okay? So x is 8, y is 1. I'm going to write them together. I'm going to box it up. All my work is shown. My answers are boxed. The teacher can find them. All is good. Now, if we have time, we want to check, right? Let's check. Quickly, 3x plus y has to equal 25. So that would be 3 times 8 is 24, plus y is 1. 25 equals 25. So the opposite sides are congruent. 2x has to equal 16y. So 2 times x is 2 times 8. That's 16. And 16 times 1 is 16. So I know that those are congruent as well. So everything checks out. We're feeling confident that we have the right answer. All right. Now it's time for the program, part of the program we call the Say What? Today is just going to be a nice application of what we can do with quadrilaterals, or any polygons really for all that matter, or diagrams. And it's called tessellations. Okay? Here's what a tessellation is. A tessellation is basically created when a shape is repeated over and over and over again, covering a two-dimensional plane without any gaps or overlaps. Now, tessellation is sometimes called a tiling, and here's why. Tessellation comes from the Latin word tessera, which literally means a stone. And reason being is these tessellations were originally made up of stone or ceramic tiles, and they were used to create mosaics, pictured mosaics, on the floors and on the walls of Roman buildings. Okay? So we've retained the tessellation or the root of tessellation from a mosaic, and now we use it in a geometric sense to cover a plane with a geometric shape. Okay? Now, creating tessellations is an entire show in itself. It can be fun, it can be time-consuming, we don't have time, so I'm just going to give you some examples here. This tessellation is made up of a bunch of triangles. Okay? And what I mean by, again, a tessellation is I'm taking triangles and I'm just rotating them or translating them, and I'm basically packing them in together, and I can continue this pattern indefinitely, and I will cover the sheet, basically this sheet of paper if I continue the pattern. The different colors are there just to make the pattern look a little prettier and to show the contrast from one triangle to the next. This one here is made up of parallelograms, okay, and specifically of our old friend Mr. Rhombus, okay, and basically it's taking these diamonds or these rhombi and it's rotating them around, and again the colors make it a little prettier and it shows the contrast. But these shapes pack in this surface. They tile the entire sheet of paper if they were extended out. Now you might see these patterns in construction quite a bit. This is a pretty common pattern made with rectangles. It's called a herringbone pattern. And anybody who lays tile is very familiar with the herringbone pattern. It's just using rectangles in an alternating switchback fashion to cover a floor, to cover a wall, to cover a sheet of paper. A herringbone pattern. Okay? Now, there is a famous mathematician, although he denies that he ever was a mathematician. Math people tend to give him credit. He was really the most famous graphic artist, or one of the most famous graphic artists of all time. His name was M.C. Escher. Okay? And he lived from 1898 to 1972. What he did is he incorporated a lot of geometric concepts, especially tessellations, into what he called his symmetry drawings. Okay? And there's a website here, his official website, www.mcescher.com. And there's a lot of information about the man, M.C. Escher, his work, when he lived, where he lived, and a lot of examples of his artwork, which include many tessellations. I have a couple to show you today. This one here is a tessellation. He called this one symmetry number 20. It has nothing to do with really what the concept is other than a symmetry drawing or a tessellation. It has fish, okay? And he started with a basic pattern here. This is not a quadrilateral. It's actually a diagram of fish. But he used the fish in such a way that if he rotated it, he could basically tile the surface or pack in the surface using nothing but fish. And they all fit together seamlessly without any gaps or overlaps, okay? This one here is interesting. He used birds, and he basically tiled it with a morphing aspect. So one was getting larger while the other was getting smaller. He morphed a bird into basically some rhombuses here, or parallelograms, into a village. And this one here is my favorite. This one actually has some, it's called Reptiles from 1943. He actually has little lizards that he tiled this page with, and just to make it more artistic, he has the lizards crawling out of one side of the page, all the way around and crawling right back into the tessellation. Okay? So a fascinating man, a brilliant artist, and really a brilliant mathematician. All right, weren't those some cool pictures at the end there? Who said math can't be beautiful, right? There's a lot of artistic impression in mathematics. So you just have to go out there and look for it. So hope you learned something today. Hope you have a new appreciation for some of the applications of geometry. And until next time, as always, I'm Kevin Corpy, and I'll catch you on the flip side.
You're watching at Channel 98